Greetings again, everybody. So we have finished talking about how to solve the systems of differential equations. So now, in all of our examples, we considered several different cases where the system may end up from non-zero initial conditions, okay, the free response, or the forced response where we don't have initial conditions. They are all zero, but the system has some sort of input, being fed into it. And then, of course, we had the combined situation where we had both non-zero initial conditions and some sort of input. So, for the free responses, we saw a case where the system may start from some non-zero point, and then what we saw that the system steadily went into zero. We saw another example where the system started from zero and ended up in a non-zero point, right? Of course, we saw the combined case where the system started from a non-zero point and ended in another non-zero point where we had the combined response, something like that. And of course, there are several other situations to consider, not just the case where we don't have oscillation, but also the case where we have oscillations, right? So we may end up having something like that. All right. Or in the case of an impulse response, we saw something like that. Okay. Surely. And again, if I have a free response, but I may have complex poles in the system, I may end up seeing something like that. Oops, I'm sorry. All right. Come on. My apologies for this. Okay. So several different situations. And all of these are system responses. Okay. So these types of responses, in these types of responses, we studied two different major characteristics. Okay. The first characteristic is the so-called, or the first part, if you like, of the response is the so-called steady state response. Okay. So now, as the title says, the steady state response refers to the part of the response. Some words may say the part of the response that doesn't go to zero, but I think it's better to say that it is the part that corresponds to the response after the transition, the initial transition has been performed and is finished. So basically, by steady state, we refer to where the heck does the system end up after its initial transition. So, for example, this system ends in zero. This system, after its transition, ends up in this non-zero position, right? And the same for this system, after some transition, it's ending up in this point, right? This system as well, it's ending up, the system ends up here, the system ends up here, and this system again ends at zero, and this again ends at zero. So the steady state, gives us information about where the system is stabilized, after it's performing its transition from its initial position, from its starting point, where the hell does it stabilize? Okay, so this is the steady state. Okay, it's basically the part of the response that doesn't go to zero, but that's a bit more difficult to understand. Okay, so we study the steady state response of a system, especially under specific inputs, to be able to understand where the system will end up with. And especially in automatic control systems, we may, for example, no, this doesn't have to be dust. We may, for example, provide the system with a set goal, something like that, and we want to see if the system is in a position to reach this goal. So will it eventually reach this goal, or should we have a possible error between what we want to reach and what we are eventually reaching, whether we perform an oscillation or we don't perform an oscillation. So that's why we study the steady state response of a system, to get an idea of whether the system can reach the desired state. Okay. Now, what about the first half? Okay, the first half actually refers to terms in the solution that eventually die out, they go to zero. And this is the transient response of the system. Okay, and the transient response, gives us information about how the system transitions into its final position. I mean, does it transition by performing this steady transition without oscillations? Does it transition by doing oscillations, just like in this case? And also, how? Not how, how long are the oscillations, so how short. So, you may end up having many, many different situations where you either have an oscillation or you don't have an oscillation, but again, you may transition very fast. You may take a lot of time to transition, or many, 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 many seconds to transition, or you may have a very short oscillation, or maybe a very big oscillation. Okay, that takes a lot of time to die out. And all of these, characteristics are characteristics that are given by the transient response. Okay, so this is what the transient response refers to. Of course, if I write down the solution of the system, especially, for example, this is the case under a step input, so you will see that this term doesn't die out. So this is a term that corresponds to steady state behavior, a steady state response. And this is a term that eventually dies out. So this term corresponds to the transient response of the system because this eventually goes to zero. Okay. But of course, there is another very big question here, which is how do we know where the system ends up in? Okay, so the system, uh, oops, I'm sorry, as we saw in all of our examples so far, always ends up in a position, either a non-zero position or the zero position. But it is possible that the system will not go to zero or to a steady position, but maybe it will go, towards infinity. So what would happen if the system goes to infinity? Right. So if we had something like that, we would have the so-called instability. And this is an undesired behavior because obviously when you're studying a system, you don't want the system to end up going to infinity. Plus or minus infinity doesn't matter. So a question before going into the process of studying transient and steady state behavior is basically how do we know when a system will go to zero or not? And this of course refers to any type of input and any type of initial condition. So we are studying the stability basically as a fundamental concept by looking at the free response of the system. So we're not studying the stability under a specific input. We want to generally look at how the system will behave if we simply give it some initial energy. Okay. And in order to do that, we look at the so-called characteristic polynomial of the system. And basically, the characteristic polynomial of a system is the polynomial of the denominator of the transfer function. Okay. So we have any given transfer function, we have a numerator and a denominator. Okay. And this denominator right here is the so-called characteristic polynomial. Okay. And we are studying this polynomial. Let me write it down. Okay, in order to understand how the system will behave. Okay. Now, of course, you might be thinking I'm crazy because I just said that for stability, we are studying the free response of the system. So you are thinking, Lazarus, I mean, you're talking about the free response, but at the same time, you give us transfer function. But the transfer function gives us a relationship between input and output. So this doesn't make any sense, right? No, let me explain. The characteristic polynomial appears irregardless of the input of the system. And that's why we look at it. So, very simply put, let's consider a differential equation. Okay. I'm going to give a random example of a differential equation. And this is u of t. Now, mind you, u is any given input. I don't care what the input is. So let's see what happens. Let's say we want to solve the system. Okay, we take the Laplace transform, and this gives us this analytical expression. Let me write it down. I'm going to write any possible term, okay, because I have made no assumption on what the input is and what the initial conditions are. Plus 3 times sx of s minus 3x0 plus minus 2 x of s. This is equal to u of s. Now I'm going to factor all the common terms here. So this will give us s squared plus 3 times s minus 2 over x of s. And this is equal to, let's see, s plus 3 x0, okay, plus x dot 0 plus u of s. Okay, so we have all of these terms here with regards to initial conditions and the input. And then let's, send this term right here, this factor, on the other side of this equation, and we're going to obtain s plus 3 x0 plus x dot 0 over s squared plus 3s minus 2 plus u of s over s squared plus 3 of s minus 2. So this is what happens. You see, both of these terms, one of these fractions depends on the initial conditions and the other depends on the input. See, any type of input. So I haven't replaced the Laplace transform of the input. I don't care about it. What I only care is to explain you this. Look at both of these fractions. Their denominator is the same. Okay, and this denominator, of course, is also the denominator of the transfer function. I mean, it is very easy to understand that here the transfer function is x of s over u of s, and it is 1 over s squared plus 3s minus 2, right? Which we can, of course, break down into individual fractions. And these fractions are the natural response terms. I think that's how you usually call them in English textbooks. And the important thing is this. Irregardless of the initial conditions and irregardless of what the input is, the partial fraction of these two polynomials will tell us if the system will or will not go to infinity for any possible initial condition, for any possible input, right? So let's say we're looking at the free response. So let's say we don't have any input, so this gets removed completely. And let's say we are given the initial conditions. So what do? We do a partial fraction expansion. Depending on the polynomials in the denominator, we're going to get terms that go to 0, or we're going to get terms that go where? To infinity, right? So let's say we end up in a situation having this sort of term right here. Let's say we have some alpha over s plus 2, right, plus beta over s minus 1. And then what this will give us by the inverse Laplace transform? One of these terms is going to be minus 2 of t by u, and the other term is going to be plus t u of t. And this term goes to infinity, right? So if this term appears in the characteristic polynomials, we will have instability. And this will appear, and instability will happen regardless of the initial conditions and regardless of the input. Again, if we are talking about step response or an impulse response, we are going to cross this term because we don't have initial conditions, they start from 0. We are going to replace the transfer function of this input, any type of input, and then we are going to do partial fraction expansion. But the roots of this polynomial will appear in this partial fraction expansion, okay? So they will definitely determine the stability of the system, okay? So this is why when discussing stability, we always look at the so-called characteristic polynomial of the system. And this is, of course, the same as the polynomial of the denominator in the transfer function. Okay, so in the next video, we're going to discuss all the possible situations for the poles of the characteristic polynomial. And based on these poles, you will see that we will either end up with stability or we will end up with an instability in the system. Okay, so any questions that you have, you write them down in the comments. Thank you very much.